So here's another example. These are more interesting word problems, more challenging. But we've learned how to use dimensional analysis now, and so we can figure these things out. And this actually relates to a density problem as well. Titanium bicycle frame contains the same amount of titanium as a titanium cube measuring 6.8 centimeters on a side. And they've given you a picture. Pictures can be really helpful. If they don't give you a picture, you can draw your own picture if you're not good at making pictures in your mind. So what's that sentence saying? It's saying we've got a metal bicycle frame made out of titanium. Same amount of titanium as would be in a cube this size. And it says use the density of titanium to calculate the mass in kilograms of titanium in the frame. And then it asks, what would be the mass of a similar frame composed of iron? So we're going to need the density of titanium, aren't we? It says use the density of titanium. So let's go find that right away. Back here, there we go. There it is. Titanium, 4.50, and the unit is grams per cubic centimeter. So 4.50. So I'm going to write that down. Density equals 4.50 grams over cubic centimeters. That's the density. What sort of information are they giving us? Well, they're giving us this dimension of a cube. And they're asking for what? The mass in kilograms. I'm not wondering what to do. I'm just trying to figure out how to tell you what to do. So we have the density here. The density allows us to convert between grams and cubic centimeters, right? But we need a volume if we're going to convert to the mass. How can we find the volume of titanium in that frame? Yeah, we need to cube 6.8 because the volume of a cube is the length times the width times the height. If all those are equal, then it's just that one dimension cubed. So it's 6.8 centimeters times 6.8 centimeters times 6.8 centimeters. So 6.8 times 6.8, so I'm using my phone because I'm too lazy to walk over to my bag and get my calculator. 314.432. What would the unit be? Centimeters cubed, not just centimeters. How many significant figures should that volume have? 2. Because the number that we're using is 6.8. That has 2 significant figures, and we're multiplying it. And so the answer should have 2 significant figures. Do we want to round it off right now? No, because this is not our final answer. What I do is I underline the uncertain digit, which is the last significant figure, just to remind myself of how many sig figs this thing has, so that when I do the next calculation, I don't have to go back any farther. So that's the volume. Could we convert cubic centimeters into grams? We've got the density. The density relates the grams and cubic centimeters, right? We can use that as a conversion factor to go from cubic centimeters to grams. Does that get us the answer that the question wants? Kind of. It gives us, it wants mass, but it specifies a unit, kilograms. Can we convert grams to kilograms? Yeah, we can. So our path is going to be cubic centimeters to grams to kilograms. I'm going to get rid of this picture because I need the space. Because the picture was useful, but I just don't have enough space. Ta-da! Isn't that fun? So I want to go cubic centimeters to grams to kilograms. So I'm going to write down what I had here for the volume. 314.432 cubic centimeters. And I'm underlining the 1 to remind myself that number has 2 significant figures. Now I'm going to multiply by grams over cubic centimeters, and I'm going to multiply by kilograms over grams. So our path was cubic centimeters to grams to kilograms. And so in our equation we want cubic centimeters to grams to kilograms. I put centimeters cubed down here because I want them to cancel out with that one. I want those to cancel, and I want grams to cancel grams. Have all the units in there first, and then go put numbers in. Grams per cubic centimeter, well, that comes from the density. 4.5 is with grams, and so we're going to put 4.5 with grams on top. Kilograms to grams. What does kilo mean? 10 to the 3, right? Kilo equals 10 to the 3. So since kilo is written on the top, I want to write what it means on the other side. Because all of our conversion factors have to equal 1, right? What's on the top has to equal what's on the bottom. Gram over gram is 1. Kilo over 10 to the 3rd is 1 because kilo means 10 to the 3rd. So we're going to get him in there. And then when we put that in our computer, in our calculator, we want to use 1 times 10 to the 3rd because then we can use scientific notation. So get your calculator out. If you forget your calculator, you may certainly use the calculator on your phone. I just don't want you to use the calculator on your phone all the time because you cannot use it on an exam. And so you need to know how to talk to your calculator. And calculators can be really picky. So 314.432 times 4.5 divided by, and then put that in as 1 EE3. And I come up with 1.4 something. 1.41944. And the units there will be kilograms. How many sig figs should that answer have? 2. It's limited by the measurement of the side of the cube. The 6.8 has 2 significant figures. The density has 3, but we're limited by that guy. So 1.4 kilograms. That's the mass of the bicycle frame made out of titanium. Any questions? Either it's just really, really clear, or it's really, really not clear. Yes? Okay, let's check your calculator. So, yeah, we'll do that. Okay. So then I get to colors. I'm sure there's a better way. but that's a good enough way. Okay, so what if we approach this from the standpoint of algebra? It's asking us to calculate the density. I'm sorry, not the density. It's telling us to use the density and calculate the mass. And so if we're doing density, then we need to know that density is mass divided by volume. That's just the density equation. So they're telling us to use the density. We can go look that up. The density, we looked it up earlier, 4.50 grams per cubic centimeter. And it's asking us for the mass. Oops. Right, the mass. Oh, we didn't finish the first problem. Oh, well. We'll go back and finish it. Find the mass. Okay, the density equation has density and mass and volume. So we can rearrange this equation. We can solve the equation for mass and see what mass equals in terms of volume and density. So let's do that over here. Density equals mass over volume. If I want mass by itself, that means I need to get rid of the volume on the right side. And so if I multiply by volume and do that on both sides, these volumes cancel out. And that's how we rearrange equations. Now we have something that says the mass equals the volume times the density. Well, we know the density, we don't know what the volume is. So, can we figure out the volume? Yes, we can, because we've got this cube that's 6.8 centimeters on a side. So we have to calculate the volume separately. The volume is 6.8 centimeters, that whole thing cubed, or same thing, 6.8 centimeters times 6.8 centimeters times 6.8 centimeters. And if I lose you anywhere along the way, just let me know. So we did that math earlier, and that was 314.42, right? 432, thank you. I got most of it, that's pretty good. 432 cubic centimeters. That's the volume. Sometimes you have to calculate pieces separately. So volume times density, the volume was 314.432. That's not enough room to go down a line. So this equals 314.432 cubic centimeters, always, always, always put the units in there, times the density, which was 4.50 grams over cubic centimeters. We see that the cubic centimeters cancel out. I can't remember the numbers. 314.432 times 4.5 equals, come on calculator, you're brand new, you shouldn't have problems like this. And so this is 1414.944. What's the unit on that? Grams. Just catching up with our significant figures, which I overlooked. The volume had 2, and it still had 2 over here, which means that our mass has 2 significant figures. Why didn't I get the same answer? I still need to convert to kilograms. So we can take that, and I have no space. So we'll go up here and get rid of those guys. We don't need them anymore. So we're going to take this 1414.944 grams. We're going to convert to kilograms. So we multiply by kilograms, the unit that we're going to. We divide by the unit that we start with. Kilo means 10 to the third. We put it on the side, on the other side of the line. And when we do that, we end up with the same answer. Some of you might think that method's easier. Some of you might think the first method's easier. And a few of you may think that neither of those methods is anywhere close to easy. Any questions? Yes?
Yeah, I kind of got lost in measuring one more.
When I went up here? I'm sorry, I'm in the wrong, I've got two panes here and I keep clicking on the wrong part. When I went up here?
Yeah.
Okay, so this, I am just taking this number from the bottom and moving it up here because I ran out of space. And this is grams, but the question tells me I need to find the answer in kilograms. So I'm going to convert to kilograms. Grams to kilograms is one step. We multiply by kilograms, we divide by grams. And then kilo, we write what it means on the other side of the line. Kilo means 10 to the 3. And so that's how I end up with 1.4. Did that answer your question? Okay. Anybody else have any questions? When you have a problem like this, it's a little more involved. You read through it, and it may not be obvious what you're supposed to do. Don't give up on it. Okay? Be persistent. Work at it. Work at it forwards. Work at it backwards. If you're not getting anywhere, go do something else. Your brain will keep percolating on it. And then come back. And then your brain may come up with the approach that you need. But don't just give up because it doesn't make sense immediately. Now, we haven't answered the other question in there, have we? I'm wondering if I can go back. No, I don't think I can. That's okay. So the other question is, what would be the mass of a similar frame composed of iron? Well, what's the difference between iron and titanium in terms of this calculation? The density. So what's the density of iron? Oops, passed it up. Iron, 7.86. Okay. So the density now for the iron problem, density equals 0. Sorry, that would be crazy. 7.86 grams per cubic centimeter.
Where'd you get that from again?
I got that from the table of densities, which is in a previous slide. It's also in your textbook. So sometimes you have to go look up a constant somewhere else. We previously figured out that the volume was 314.432 cubic centimeters. I really need to rework this slide. But I think I need a second slide without the picture, because the picture's really great for about 15 seconds. That's just a real pain. There we go, picture gone. So we have density, we have volume. We're going to start with the cubic centimeters. We want to end up with kilograms. So I'm kind of rehashing what we did the first time in case you didn't quite get it. So we're looking for kilograms. We got the volume from this information up here. So this guy has two significant figures. We just calculated the volume of a cube. So we have cubic centimeters and we have a density. Density is going to be used as a conversion factor, not as our starting point. So the volume is the starting point. The density allows us to go from cubic centimeters to grams. And then we need to apply another conversion factor to go from grams to kilograms. So 314.432 cubic centimeters. We have two arrows in our path, so we have two fractions in our equation. The path says cubic centimeters to grams to kilograms. So on the top of this business that we're doing here, we've got cubic centimeters to grams to kilograms. Then this unit comes into the denominator, cubic centimeters, because we want those to cancel out. And gram comes down here, so they cancel out. That's how we set up the units. Is that making sense? For the numbers, well, we've got this density, 7.86 grams per cubic centimeter. So the number goes with grams, 7.86. And then this guy over here, kilo means 10 to the third, so we write the mathematical meaning on the other side of the line. So let's just illustrate. If we had grams over grams, that would be equal to 1, right? Anything divided by itself is 1. If we had kilograms over kilograms, that would also be equal to 1. What if we write something that means the same thing as kilo, but doesn't look like kilo, but it's the same function? What if instead of kilo, we write 10 to the third? Kilo equals 10 to the third. So that's still 1, isn't it? Isn't that beautiful? It works with all the metric prefixes. Centi is 10 to the minus 2. Milli is 10 to the minus 3. You memorize those, like most of you have, and then you can make up metric conversion factors all day long for any combination of any metric unit. It's a beautiful, beautiful thing. Once it clicks, once you see it. Kilo means 10 to the third. Kilo times gram is equal to 10 to the third times gram. And so if I put kilogram on top and 10 to the third grams on the bottom, then it's going to work out, and I'm going to get the right answer. Okay, so we do the math there on the calculator. 314.432 times 7.86 divided by 1 EE3. There's no times 10 or anything in there. And the calculator is showing me 2.471435552, and that will be kilograms. I'm supposed to have two significant figures, so I'm going to round that to 2.5 kilograms. So the titanium bicycle frame weighed 1.4 kilograms, and the iron bicycle frame weighs 2.5 kilograms. That's a lot more. Any questions? I'll take that as a no. Okay, so this one's fun. In 1999, NASA lost a $94 million orbiter because two groups of engineers failed to communicate to each other the units that they used in their calculations. Consequently, the orbiter descended too far into the Martian atmosphere and burned up. Bummer. That's a little bit worse than leaving your bike in the driveway and Dad running it over or something. $94 million orbiter. So suppose that the mass orbiter was supposed to have established orbit at 155 kilometers. And the elevation or the distance from the planet at which you have the orbit is really important. Because if the orbit is too far, it won't stay in orbit and it'll just fly off. And if the orbit is too low, gravity will pull too much and it'll spiral in and burn up. So that distance is really important. So it's supposed to be at 155 kilometers. So one group of engineers specified that as 1.55 times 10 to the 5th meters, which is true. Suppose further that a second group of engineers programmed the orbiter to go to 1.55 times 10 to the 5th feet. Well, we got the numbers right, we just got the little mistake with the letters at the end there. No big deal, right? Let's calculate the difference in kilometers between those two altitudes. So this is another of these kind of confusing sort of problems. Picture might be helpful. So let's draw a picture. We'll draw pictures of engineers. I'm just going to get rid of this thing right there. I don't need that at all. So over here, we have one group of engineers. It's a small group. And so they're saying the orbit needs to be 155 kilometers, which equals 1.55 times 10 to the 5th meters. And that is true. That's not an error in the calculation or anything. And then these guys over here, maybe we'll make these the yellow guys. These guys over here saw 1.55 times 10 to the 5th, didn't pay attention to the units, and just kind of assumed it was feet. And so we need to find the difference between these. Difference is just subtracting. The question wants the answer in kilometers. Can we take 155 kilometers and subtract 1.55 times 10 to the 5th feet? No, it has to be the same unit. So let's convert the feet into kilometers, and then we can do the subtracting. So what we're going to do is we're going to convert feet to kilometers, and then we can subtract. Does anybody know the relationship between feet and kilometers? I don't. No. What do we know? Well, what could we get to kilometers from? Meters? Feet to meters? I don't know that one either. Centimeters? Okay, start over, because this is getting, that's getting too long. See, the other class, somebody looked in their composition notebook, actually, and it had a conversion factor.
Feet to inches to centimeters, and go back up.
Yeah, that's what we're going to have to do. I just ran out of space. We can go feet to inches, inches to centimeters, centimeters to meters, meters to kilometers. Is this the only way to do it? No. But in the absence of looking up a conversion factor, these are things that I know in my head, so I can do this. So if you want to see the shorter way, you can go watch the video for the other class. Okay, so there's our path, really long path. We can do this, it's okay. 1.55 times 10 to the 5th feet times what unit goes on top in this first factor? Inches, right? Feet to inches. What's next? Centimeters, right? We're looking at our path that we decided on. Feet to inches to centimeters, and the next will be meters. And then finally, kilometers. Why did I choose that path? Because I know the relationships for each of these. I know that there's 12 inches in a foot. I know there's 2.54 centimeters in an inch. I know there's that centimeter to meter. Centi means 10 to the minus 2, and meter to kilometer. Kilo means 10 to the third. Is it long and drawn out? Yeah. but we're going to get the right answer. A shortcut is no good if it gets you to the wrong place. So we'll put feet in the bottom, inches in the bottom, centimeters in the bottom, meters in the bottom. Hopefully you're seeing the pattern. All the units cancel out. They all cancel out because we made them do that. Any questions about the units? So now we need numbers. We look at inches and feet. What's the relationship? 12 inches is 1 foot, right? So we need to be sure that we put 12 inches and 1 foot. Because an inch does not equal 12 feet, does it? Got to keep those units with their numbers. Centimeters to inches. That's one I have memorized. I would encourage you to memorize it. Is 2.54 centimeters equals 1 inch. Centimeters to meters. Centi is on the bottom. Centi means 10 to the minus 2. Oops, pulled down something. 10 to the minus 2. So we put it on the top. Because what's on the top here has to equal what's on the bottom here. And this lowercase c is just an abbreviation for 10 to the minus 2. So these are equal. In the last term, we've got the prefix kilo. Kilo means 10 to the third. Here it goes on the bottom because the prefix is on the top. So now we get out our calculators. 1.55 EE 5 times 12 times 2.54 times 1 EE minus 2 divided by 1 EE3 equals. So, calculator says 47.244 kilometers. That would have 3 significant figures. Can you get your calculator to give you that answer? There's a little bit of scientific notation in there, and if you're not doing it right, then you're going to end up with the right digits. You're going to have 4, 7, 2, 4, and 4, but the decimal place may be in the wrong spot. So if the decimal place is in the wrong spot, make sure that you're entering scientific notation correctly. The EE button or the EXP button stands for times 10 to the. You don't press 1 times 10 EE something. It's just 1 EE minus 2 or 1 EE3. So this is the distance that the yellow engineers were working with. Where can we write that? One guy's legs are falling off. Sorry about that. So what's the difference in kilometers between these two measurements? Well, it's 155 kilometers, yeah, it's 107, minus the 47.244 kilometers. And it ends up being, it'll actually round to 108 kilometers. Because 155 has uncertainty in the ones place, and this one had uncertainty in the tenths place, so our answer should have uncertainty in the ones place. And it was 107.7, I think, or something. So it rounds up to 108. Is 108 kilometers a small distance or a big distance? It's a big distance. That's about 170 miles. Think that's going to make a difference in an orbit? Yeah, that's a long distance. So no wonder the orbiter crashed. Details. If they did, if they did the calculation wrong and got the decimal point in the wrong place, you build this expensive piece of equipment and it crashes. They used the wrong units. and they did that? What if you're a doctor or a nurse and you use the wrong unit when you're calculating how much medicine to give someone? You could give them too much and kill them. You could give them not enough, and that might result in their death as well. Units are important, details are important, okay? Any questions? Yes?
How did you, the two, like, what made you decide that?
The two, which two?
From the four?
Oh, for the sig figs?
Yeah.
Oops, pointing at the wrong place. That's a good question. Why did I underline the two? Why did I say there were 3 sig figs in this answer? Because of what I started with. 1.55 times 10 to the 5th feet. This has 3 sig figs. This is an exact conversion. This is exact.
So the conversions, they don't count as sig figs at all?
It depends. Sometimes they do. This one is an exception. This is between the metric and the English system, and usually when you go between systems, they are not exact. This one's an exception. What if we didn't recognize that it was exact? We'd still end up with 3 sig figs, wouldn't we? Generally, and I said, just kind of as a rule of thumb, whatever number you started with when you're converting units, however many sig figs that had, your answer will have that. Usually it's your starting value that limits the number of significant figures. Not always, but usually. What I really want you to be able to avoid is writing down way too many or way too few. And I would prefer that you write down too many rather than not enough. Because sometimes students will just go nuts on rounding, and then they'll end up with a really whacked out answer because they took 0.0073649 and they rounded it to 0. You can't do that. You're always going to have at least one significant figure. So better to leave too many digits. It's easy to go back and cut off the extras. If you're rounding off too much, then to get the right answer, you have to go back and do the calculation all over again. So if you're going to make a mistake on leaving too many. Any other questions? So that's the end of the chapter. At the end of each chapter is the chapter in review. And I'm not going to read all these to you, but it just kind of highlights the things that we covered. Hopefully that will help you to know what's important and what isn't important. There's topics, like these guys, and then there are chemical skills. So these are things you should be able to do. You should be able to use scientific notation and count significant digits. You should be able to use significant figures in calculations and do unit conversions. End of chapter 2.